section 10.2, they've asked us to graph this function. Now, one thing that we know about exponential functions, this is y equals 1/3 to the x. Now, you could draw yourself a little chart here with x's and y's. Let's go ahead and do that. 0, 1, 2, -1, -2. By putting 0, 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. 1/3 squared is 1/9. -1. 1/3 to the -1 makes that a 3. And 1/3 to the -2 makes that a 9. Now, notice all of these are positive. Okay, that's relevant. So here's our point right here of reference. We're always going to have that unless it's been shifted up or down. We have, or left or right, 0, 1. 0, 1. And our graph, our exponent graph, goes up to the right through that point. We have an asymptote right here at y equals 0 because y can never be 0. Think about it. What value can you put in there for x that's going to make the y a 0? If you put in 0, 1/3 to the 0, we already did, we get 1. Okay, so it can't ever be a 0. So we have an asymptote right here. And it would go up to the right if this was greater than 1. So if this was a 2 to the x, it would go up to the right. But when we have a little fraction like this, it's going to go down. Look, we have 0, 1. We have 1, 1/3. We have 2, 1/9. Look at how tiny our values get really fast. So if we had 1/3 to the 100th power, that is just almost 0. It's such a tiny number that it's like it's 0, but it's not 0. Okay, it just approaches that asymptote. It approaches 0, but it never becomes 0. And then we have -1, 3, and -2, 9. So see, it grows really, really fast. When they say exponential growth, that's what they're talking about, is something like this. This one would have exponential decay. It goes down. Because it's 1/3, it goes down and to the right. Okay, let's look at problem number, I'm going to skip ahead to problem number 17. The reason why is because this is its inverse. If I have g of x equals log 1/3 x, okay, let's rewrite this with a y. Y equals log 1/3 x. Then I'm saying 1/3 to some power y gives me x. Well, look, that's exactly x and y reversed of this graph. Okay, so that 1/3 right there is that 1/3 right there, but in reverse. So these are inverse functions of one another. So in order to graph it, all we need to know is that an inverse, or this logarithm graph, is going to go through, instead of 0, 1, it's going to go through 1, 0. And this would rise up to the right if I had a bigger number right here. Something greater than 1. But it's not. It's a 1/3. So like this one comes down, this one's also going to go down. This one had a asymptote of y equals 0. X and y switch. So this one has an asymptote of x equals 0. And it's going to come real close to it, go through that ordered pair, and then swing out. Those are inverses of one another, and they're a good reminder of our basic logarithm and exponent graphs. Okay, that's 10 and 17. If you do problem number 9, it's just the inverse of problem number 16. So do those two next to each other, 9 and 16. All right, so let's scoot back to problem number 12. Problem number 12 says 5 to the 2x plus 1 equals 25. All right, so what we have is x in our exponent here. If I have 6 to the x equals 6 to the third, what can you tell me about x? Well, x has to be 3. Like, there's not something else it could be that this would still be true. It has to be 3. So if we can make our bases the same, then our exponents have to be equal. And so that's the way we're going to solve this. Don't do stuff to both sides of the equation on these. When your x is in the exponent, you want to just rewrite the bases. All you're doing is rewriting equivalences so that you get bases the same on both sides. Can I make this 25 have a base of 5? Yeah, 25 is 25, yeah, it's 5 squared. So all I did was rewrite an equivalent of 25. What is the same thing as 25? It's 5 squared. And then just rewrite this side exactly the same. Now that they have the same base, their exponents have to be equal to each other. So you can say 2x plus 1 equals 2, and go ahead and solve. 2x equals 1, x equals 1/2. Okay? So that's your answer. X equals 1/2. It's problem number 12. All right, let's look at problem number 14. Problem number 14 is going to do kind of the same thing here. We have 1 over 27 to the x minus 1 equals 9 to the 2x. So we've got x's in our exponent. What we want to do is we want to just rewrite equivalences of both of those sides, or one side, however you want to do it, until we can get the same base. So now 27 and 9, they both could be written in terms of a power of 3. So let's do that. 9, all we're going to do is rewrite 9 as 3 squared. 9 is 3 squared. Now rewrite the rest of it just exactly the way that it showed up. Over here, what's 27? 27 is 3 cubed. Okay, that's 1 over 3 cubed. Okay, so we're not quite there yet because we have 3 in the denominator here and 3 in the numerator here. How can I move this up to the top? With a negative exponent, right? So let's rewrite this again. This is going to be 3 to the negative 3. And that's x minus 1. Rewrite it just exactly. All right. Now, how do exponents act when it's a power to a power? When they're just touching like that? Do they add? No, they multiply. So these two things get multiplied. These two things get multiplied. This is going to be negative 3x. We could write it this way. Negative 3x minus 1 equals 2 times 2x. So I'm going to go up here. I'll go over here. Negative 3x plus 3 equals 4x. Add 3x, add 3x. 3 equals 7x. Divide by 7, divide by 7. X equals 3/7. Just kidding. 3/7. All right, that's it for problem number 14. We already did problem number 17. I'll let you do 16 in conjunction with problem number 9. Let's look at problem number 18. Problem number 18 says log base 8 of 64 equals x. And it's really important that you're able to rewrite logarithms in terms of exponential form and exponential form to logarithm. So this is the way that it looks. I have log base a x equals y. This is the base. This is the exponent. A logarithm is an exponent. And then this is, for lack of a better word, this is your answer. So I have a to the y equals x. Okay? So this little number to this power gives you this answer. So if I rewrite it, I have 8 to the x equals 64. And if you can rewrite it in terms of an exponential form, then we can just use that exact same rule that we did before. Let's get the same base. Now you could rewrite both of them in terms of a base of 2 or a base of, yeah. But all we do is change this to a base of 8. So let's make this 8 squared. This one's still already in terms of 8, so we can just say x equals 2. The answer is 2. Now look at it. It's saying 8 to what power gives me 64? You already knew that. So the evaluation of that, 8 to some power gives you 64. The answer is 2. All right, let's look at 20. This is important right here. Make sure that you know how to go back and forth. So 20 says log base x 1 over 49 equals negative 2. I'll bet you could actually figure this out without doing anything, but let's say x to the negative 2 power gives me 1 over 49. Maybe you can actually think about what this answer is without doing it, but we're going to do it anyway. Okay, so it's saying what number to the negative 2 power gives me 1 over 49? Do you know the answer? Yeah, you do. It's 7, but let's do it anyway. All right, so I want to make this just an x to the first power. I want to know x's. So how would I get rid of this negative? Okay, I could multiply it by a negative. a negative 1/2. If I multiplied those two together, okay, and the way that I would multiply exponents together is power both sides by a negative 1/2. So negative 2 times the negative 1/2 is going to be x to the 1 power. And then this to the negative 1/2, let's apply just the negative for now. If I apply the negative 1 exponent, this is 49 to the 1/2. I just used up that part right there. And 49 to the 1/2, what's the 1/2 power? That's the square root. So that is the square root. Janet. That's the square root of 49, and the square root of 49 is 7. So x equals 7. And you probably could figure that out. X to what power? What number to the negative 2 power gives me 1 over 49? 7. 7 to the negative 2 power. Alrighty, let's look at problem number 22. Some of them aren't, you can't just figure out in your head. So let's look at 22. 22 says log base k 4 equals 1. So k to the first power equals 4. K to the first power equals 4. Well, as long as you can rewrite it, then you just found the answer. The answer is 4. Right? K to the first power is just k equals 4. Yep. It's just that easy. All right, let's look at 24, and let's have that be our last one for this section. 26, you don't need to, we didn't do those kinds. So let's look at 24. 24 says in your own words, so your words might be different than mine, but it says in your own words, explain the meaning of log base BA. Okay, so remember, a logarithm is an exponent. So log base BA, then the evaluation of that would be the exponent that b to that power gives you a. So the exponent that b raised to that power results in a. You could say it however you want. That's the way I would say it. Okay, that's it for chapter 10.